everybody. Sorry for standing here like this, but I didn't know. So we're going to do it Wolfgang Lück style and sort of do the announcements, say after the first talk, maybe after the second talk, and now just essentially start the mathematics. So there's the first two talks will be by Frank Quinn, and your stage.
Well, I would like to thank the organizers for this opportunity for us all to explore some beautiful mathematics. And let's see. The first question is that visible? And is it different from that? Yes? No?
Visible.
Hmm?
Definitely visible.
Visible, okay. Well, I'll not use it in a way that's really important to see. Is it, well, that visible and different? More different. More different. Oh, okay. Okay, so my topic is to give a description, a geometric description of surgery, basic material of surgery. And I want to diagram the subject. So a box is explored, cloud is still mysterious. So I should say there's a lot still to do in here. So I will, in the course of the lecture, describe some of the things that are left to do and give some reasons why they were worth doing. Okay, so first of all, there's classical surgery. Then there are symmetric chain complexes. The theory developed by Minsky, which gives an algebraic description of the obstructions in surgery. Then there's some more geometric things. So there's a lot, I mean, there's a basic material needed for the development is known, but there are some loose ends in Poincare normal spaces. Then there's some sort of generalized confidence. Which is also got some mystery to it. And this is a stable homotopy formulation that if you apply chains to it gives you the change here. And the reason that I want to interpose a geometric thing, a homotopy chain, is that you can apply different homology theories. So if you have a spectrum, well, I guess we would need a fancy ring spectrum. You get some sort of spectrum, symmetric spectrum. And then, okay, and this is really not fully worked out. And this is the case where the spectrum is so this is appropriate for homology with coefficients in different spectra. So if you want point array duality in K-theory or with the L spectrum or some other thing, then you can do this. And one of the reasons for doing this is that there is a connection with intersection homology. Which is well explored. And this would give a version of intersection homology for different spectra. One of the things that's not apparent right away when we're talking about manifolds is that this theory really has to do with the structure of point array duality. And if you have something that has a duality homomorphism, well, what do you do, or duality map, what do you have to do to make it into an isomorphism, so you have a point array thing. So it's about exploring the failure of duality. And the homology of, for example, a stratified space or an algebraic variety or something like that doesn't have duality, but it has a isomorphism, but it has a duality homomorphism. And you can ask what are the obstructions to making that algebraically an isomorphism. And the answer is intersection homology. And you can play similar games with other spectra. And a particular thing that is interesting or important is homology of a manifold with coefficients in L spectrum. If you have a topological manifold, it's pretty nearly, topological manifolds are pretty nearly characterized by having a duality with coefficients in the L spectrum. So somewhere in here is the Renitzky single obstruction. And there's an important story that has to do with that as well. The Renitzky single obstruction gives a very powerful characterization of topological manifolds along these lines. And something that would be extremely useful is a similar characterization of smooth manifolds. And I'll say a little bit, well, maybe I'll say a little bit towards the end, at the end, about what would be necessary to make that work. I mean, just as an illustration, if we have an algebraic variety, we can figure out when it's a topological manifold, but we can't identify whether or not it's a smooth manifold unless we know it to be non-singular. So there's a hole there. Okay, so I want to start with at a very classical place, and describe the classical theory for manifolds. And then we'll see this unfold as we go along. So the classical theory I want to say a word about this. It's complicated. And what that means is that it's not a sort of philosophical thing or a conceptual thing. It's driven by the details and optimized. So the shape of the theory is really determined by the technical ingredients. And there's a certain amount of manipulation you can do to try to adapt it to one situation or another. So this, the starting point, I'll describe an optimized version and I'll describe some of the details that go into it. But it's not, you shouldn't think of it as a sort of engraved in stone thing. As I say, you can tinker with it to change it in various ways according to your particular needs. All right, well, the surgery sequence. In the surgery sequence, the ingredients are M is a category of manifolds. So that's diff, T, L, or top. D is called the decoration. It has two flavors in the usual formulation. H means homotopy equivalent. And S means symbol. Homotopy equivalent. So somewhere in here there will be some homotopy equivalences. And the decoration indicates whether they're simple homotopy equivalences or just homotopy equivalences. X is an n-dimensional Poincare complex. S stands for structures. N stands for normal maps. And L stands for L. So I'll define S and I'll define N. And you can think of this as something you really like to know, and this is something that's more accessible. So what you'd like to do is start here and figure out what you have to do to get back in here, and the exact sequence tells you that. So there's a sigma surgery obstruction. and then eta associates to a structure its normal map. A Gaussian, this is an exact sequence of sets. So what that means is Ln plus 1 acts on the structure set, and the quotient injects into N. So that's exactness here. Then exactness here is that the image of eta is the inverse image of 0. So this is actually a group. It has a 0 in there. And the inverse image of 0 in here is the image of this. This is not a homomorphism, so it may be that there's nothing in the inverse image of 0. So that's a sort of basic awkwardness. And we'll find a sort of athon structure on here in some cases that makes it a little more organized. Okay, so I'm going to first define the structure set. So it has objects, and then there's an equivalent relation. Now, objects are maps F from M to X, and remember that X is n-dimensional Poincare space, and with fundamental class. Now, in general, we'll be using z pi 1 coefficient, so the fundamental class is in the universal cover, or twisted. This might be twisted. So this fundamental class it's supposed to be in Hn of X, but the coefficients might be different. Well, don't really need to go into detail about that. I mean, you probably all do enjoy homological algebra over group rings, but it's a complicated thing, and we don't really need to go into that here. Okay, so F is a degree 1, it's a homotopy equivalent. With either simple or ordinary homotopy equivalent, depending on the decoration. Again, I'm going to just drop the decoration because I'll be formulating it in a way that really the decoration is inert. You go back and add S's everywhere or H's everywhere, and it's okay. This is a homotopy equivalence, and we want that the image of the fundamental class of M is equal to the fundamental class of X. And M is a manifold, M manifold. Smooth, PL, or topological. Okay, now, I mean, this is sort of a philosophical point. If you have a fundamental class here, then image will be a fundamental class for X. If you have a fundamental class here, then there's a unique one. I mean, you know, F star on the homology is an isomorphism. So fundamental classes for X correspond to fundamental classes for M. When we go a little further, we will be in a situation where we'll be assigning the fundamental classes separately, and we will need this condition. Here, it's sort of, in some sense, not necessary because there are only basically two choices that they're determined. So this is degree 1. The other possibility is degree minus 1. Okay, so that seems like the thing, right? You specify the homotopy type and you find out whether or not it's equivalent to an manifold. And this is, okay, in M X. Oh, I should say, those are the objects. The equivalence given by the same thing over X cross I. So W, boundary 0W, boundary 1W, X cross I, X cross 0, X. Homotopy equivalence of triples. And this is going to turn out to be very powerful, actually, that we're using sort of the same things for equivalences. Okay, the normal map set is the objects are maps. So F, B, there's some more data. C, where C is an M bundle over X. So we don't want to get into too much detail about what bundles are. You can think of micro bundles. This is a solved thing. So for smooth manifolds, we have vector bundles. Great. For PL manifolds, we have block bundles. For topological manifolds, we have, well, whatever. A little not entirely clear. But the stable theory, those are unstable things. The stable theories are soft. They're just micro bundles. So I'm not going to be specific about what a bundle is. And one of the points is that, well, I'll say that in a minute. So F is a degree 1 map. M is a M manifold. This is the M normal bundle. And some big N plus K. So it would have fiber dimension K. That should be white. And generally, we'll think of K as much bigger than N. So that puts us in some kind of stable range where the exact details of the bundles are not too important. Everything can be done using microbundles. This is, B is a M bundle map. Maybe a better way to state that is that you can take F and pull back C, so that's over M. And then here we have nu, the normal bundle, and then B is an isomorphism. So it's an isomorphism composed with a pullback. So that's what I mean here by and this apparatus is called an M normal map. So the normal refers to this bundle business about the bundle. So I want to define a function f m in, I should say, equivalences are the same over x cross I. So over x cross I, you'd have a thing with boundary. So you'd have manifold with two pieces of the boundary mapping to the ends of x cross I, and so on. So I'll come back more detail about that in a minute. So if M acts as a homotopy equivalent, then, so this is F, then we have a homotopy inverse. The only thing we're missing is this bundle information. Well, the normal bundle of M is isomorphic to F inverse composed of F star, normal bundle of M. This is the identity. Let's see, here.
It's good.
They have them out of order?
Yeah, it's good.
Oh, good.
No, it was good.
Okay, well, this is, pullback is contrarian. Right. So this is F star of F inverse star of nu M. And so I can take this to be C. So this is, there's no content here. We have a bundle here. We want to pull back of one here. Well, we just push it forward and then pull it back. The homotopy equivalent, the bundles correspond. So there's a normal. So M F Okay, so here's the comment, is that the role of the bundle. In the early versions of surgery, Currier and Miller and some of the other things, early without. So there's a sort of basic construction for doing surgery, studying the kernel and co-kernel, or fiber and co-fiber of this thing. And if you try to do this without the bundle information, what you see is that you keep hitting obstructions that relate to bundles. So include the organized disease. I think it was Browder and Wall figured out that you could avoid getting bundle instructions during the construction by assuming the existence of a bundle here, and then the instruction becomes very uniform. In particular, it doesn't depend on the category. What we'll see is that there are three versions here. There are actually 4 or 5 if you include homology manifolds and things like that. They all have the same surgery instructions. The surgery instructions don't depend on the category because the smoothness or PLness or whatever is incorporated in the bundle. So that makes it very much more uniform to have the bundle there. And you could separate it into 2 problems if you want, finding a bundle and then trying to do surgery. And that avoids the bundle instructions in the technical construction. So this is an example of where probably wasn't our first choice to do this, but this is what works. All right, let's see. Where do we go from here? Yeah, I want to describe relative versions. The idea is that these are qualitatively the same, but they're really essential. Well, they're qualitatively the same with more notation. So sometimes people will just present this thing for closed Poincare spaces and say, well, the relative thing is just the same, lots more notation. That's a sort of philosophically true, but it's the relative version that where the technicalities come into play, and so, you know, like it or not, we need to do that. Okay, so here's the context. X is so this is going to be Poincare triple. maybe I should start with describing what a manifold triple is. Well, that didn't work so well. Okay. So the picture is like this. Here's M, and then the boundary is divided into two pieces. Boundary 0 M here, boundary 1 M here, and then there's an intersection. And the idea is that this should be a manifold. M has a boundary. Boundary 0 M union boundary 1 M. So together these pieces give you the whole boundary. And each boundary I M comma intersection, so that's boundary 0, 1 M is an n minus 1 manifold. So the boundary has two pieces. Each of those is a manifold, and they're glued together along their boundaries. So boundary 0 and boundary 1 have the same boundary. They're glued together, and that's the boundary of M. Okay. Move forward. Well, maybe I can finish the sentence. So a pointwise triple is the same sort of thing. X, boundary 0, X union boundary 1, X is a pointwise with a hair. So the cohomology of X boundary is isomorphic to the homology of this X, and so on. And then boundary I X, boundary 0, 1 X is n minus 1 pointwise here. And then I wanted to find a relative structure set. M. I really need more room. So I'm going to define relative structure sets where you have a manifold with two pieces of boundary mapping to a pointwise space, two pieces of boundary. And we'll put different constraints on the two pieces of the boundary. One of the pieces of the boundary is supposed to be fixed. So you specify a structure on one piece of the boundary. not as good as the one at Max Planck.
Do our best. We do our best.
Yeah, well. Fun problem, I'm sure. Well, I think I'll be sorry if I don't let it dry, so maybe I'll just erase over here for a minute. I think actually instead of defining relative structure sets, I will state the pi theorem, which is the technical driver of this part of the theory. Okay, so suppose this is the pi here, and this is, as I say, this is the technical driver of the structure of this part of the theory. So suppose we have W, boundary 0, W, boundary 1, W, okay, so here's F, and then we have these C and an M bundle over X, and B is an isomorphism. B is a bundle isomorphism of the normal bundle of M with S star. Now, the normal bundle of M is rail boundary. So, if we have, if this is M, here's boundary M, the normal bundle is a bundle over M. Well, one way to think of it is you can take M and embed it so the boundary is in the boundary that is Dn plus K. And then the normal bundle is a regular neighborhood.
So N means W, right?
Well, I'm thinking of M as having dimension n.
Zero starting.
The what? Oh. Well, this is just discussion for the normal bundle of a manifold boundary. Okay. Manifold is M. Unless, I mean, the reason I have a different letter here is that eventually I'm going to, one of these boundary pieces is going to be M. Okay? So that's the benefit of writing notes. So you can look ahead and see when you're going to have a collision of notation and change a letter. So I've done that. But I didn't do it here. Right, okay. This is, that would be W2. All right. So there's not anything weird going on with the boundary. I mean, it's just a button. Okay. So this is the normal part, and then the data, as before, is that this is an M manifold straight line. This is n-dimensional Poincare triple. F is degree 1. So the fundamental class of W is in the relative homology. And we want the image of that is the fundamental class of the Poincare space in the relative homology of X. Let's see, degree 1 normal. So far, this is just the same as before. Now the active ingredient, we assume that boundary 1 W with its boundary this is a homotopy equivalent. So it's a homotopy equivalence on part of the boundary. The second is, this is why it's called the pi-pi theorem. Pi 1 of boundary 0 and the pi 1 of X is isomorphic. And then n is figure 6. At some point, we may need to negotiate about that. But anyway, these are the basic conditions. And the conclusion is that this is equivalent in the sense of a similar thing over X cross I. So this is then there exists let's see, W. I need a new letter. V. V. V to X cross I. So this has, what is this? This is X boundary 0 X boundary 1 X cross I 0 1. So I guess this has 4 pieces of the boundary. This is normal. So this is when we cross with I, it's an n plus 1. So this is n plus 1. And so I'm not going to introduce notations for all the pieces of the boundary. We have a notation problem with boundary 0 and boundary 1 and 0 and 1. So if we get into the space versions, I'll have to fix that. But right now, just skip it. So anyway, this has 4 pieces of boundary, degree 1, normal, and V, let's call now gives us the boundary, boundary 0x cross I, boundary 1x cross I. X cross 0, and I'm going to call this boundary 0 with curly braces around it. And X cross 1. So how about boundary curly brace 1? So here we have four pieces of the boundary. Boundary 0, boundary 1, boundary curly 0, boundary curly 1. And we want boundary curly 0 of V to be the original starting data. I'm going to draw a picture of this thing in a minute. W. So over 0, we start with the original thing W. Boundary 1, V, which goes to boundary 1 of V is boundary 1 X cross I. Well, this is boundary 1 of H. What was was there a name
The original.
of this map? How about H? Here's a name. F? Oh. F. I'm going to have a notation problem. When I go back to M, it's going to have map F. Okay, well, we can deal with that. Okay, boundary 1H, F. This needs a name. This is capital F. So this is a boardism of these triple thingies. Boundary 1 capital F is boundary 1 little f across the identity on I. So it's constant, where F is a homotype equivalence. So that part of the boundary is already good, we don't change it. I should be numbering these. So this thing, I'll draw the picture in a minute. Let me finish. Boundary 1 of V, that maps to X cross 1, is also a homotopy equivalence. Okay, so here's the picture. Here's boundary 1, which is nice, and then boundary 0, which is wiggly because it's not a homotopy equivalence. Okay, so then this goes by boardism. Boundary 1 doesn't change. So where it's already homotopy equivalent, it doesn't change. And then at the end, the whole thing is a homotopy equivalent. So I draw it smoother. And then in between, it might do all kinds of funny things. So there's a boardism through such objects to one that's a homotopy equivalence on this whole boundary 1, boundary curly 1. Okay, one way to think about this is, here we have a problem, a normal map, which is already a homotopy equivalence on part of the boundary. Well, there's presumably some sort of obstructions to making this thing into a homotopy equivalence. And there's some kind of obstructions on the boundary as well. Well, the idea is, if the boundary, the free boundary, and the inside has the same fundamental group, then somehow you can push the obstructions off across the boundary. So, what would give you a non-trivial obstruction here is if the pi1 is not an isomorphism, so the change in pi1 will trap something on the inside. But if the pi1s are the same, then whatever goes wrong here, you can push it over the boundary and fix everything. So the technicalities, there are a couple ways to prove this, and some of the technicalities differ from category to category, but there's a uniform output. And this is the driver. Okay, here's a corollary. So suppose we have, let's forget about boundary one for a minute. So let's see. Oh, yeah, okay. So suppose we have M to boundary 0, well, Y, and this is a degree 1 normal map. So it's an element of the normal bundle. Then we would like to know if this is normally bordered to M prime homotopy equivalent. So can you fill in between M and get a bordism from M to some M prime that would lie over Y cross I technically? This is a homotopy equivalence. Well, this says that that is implied by a much weaker thing. That you can let Y change by Poincare bordism. So you can include this as boundary 1x, boundary I think I'm going to try to get the notation right in the next lecture. But the idea is our goal is to change M by a bordism over fixed Y. What this says essentially is that you can let Y change as well, as long as it doesn't change pi1. And if you can get a bordism from My to M prime Y prime, where Y changes by a Poincare bordism, then you get a relative thing over the Poincare bordism, and then you can push across, solve that to get a solution to the original. So let Y change by Poincare bordism solve implies the original. So it can be solved. afford to loosen up what happens on the right. And I'll show you how to exploit that next time we do this on an obstruction group. Okay, so maybe we'll have a